Hello to my talk about remote scheduler contention attacks. This is joint work with Jonas Juffinger, Lukas, Maar, Christoph, Andreas, Kogler, and Daniel Gruss. So let's start with a quick motivation. Basically, it's, most of the stuff that you are doing is software related, but also the hardware is important. In particular, secure software doesn't automatically mean secure execution. So, because the underlying hardware can expose sensitive information too, and therefore security depends on both. If we talk about microarchitectural information leakage, then there might be direct leakage or indirect leakage. Direct leakage is usually a hardware bug, and indirect leakage can be observed via a side channel. There are multiple ways how this can happen, for example, via timing, by power consumption, or EM radiation. In the following, we will focus on timing side channels. First of all, a few basics about how the modern CPU pipelines work. Two threads, thread A and B, and they feed instructions into the front end. We have two threads because it's an SMT machine, and the front end then decodes the instructions into micro-ops, and these go to the retire control unit. The retire control unit then forwards the micro-ops into multiple schedulers, or on the FPU side, it's scheduling queue, and that one again forwards micro-ops into schedulers. The important thing here is, of course, we focus on Zen 3 and Zen 4. And these machines have one particular property. They have multiple schedulers, which is a little bit different to Intel, where we have only one joint scheduler for all the execution units. What's the task of the schedulers? They basically decide when which micro-op is executed on the corresponding execution unit. So it decides based on whether the execution unit is actually free and also on whether the operands are ready for execution. There are simpler micro-ops which can be executed on multiple execution units and therefore can also go to multiple schedulers. So, for example, the add micro-op can be executed on all four of the integers. But there are others that are a little bit more complicated, for example, divisions or multiplications. This has been investigated in prior work before, but the question is, are there other ones that might just go to scheduler 2 or scheduler 3? And another part that has not been investigated so far has been the floating point unit. Also, the question here is, how can we prime the schedulers for the floating point unit. Also, what happens if such a scheduler queue gets full? So here we deal with two examples. So the regular example is just, we have a little bit of space left in the scheduler queue. So the first instruction that's included into the retire control unit can be forwarded to the scheduler, and so can the subsequent one. Everything works as intended, and execution here is fast because we can now parallelize it. But what happens if the queue is full? Then basically the first instruction here has to wait, and also the subsequent instruction has to wait because there's no reordering done at this state. So the research questions that we dealt with in our paper, there are 4 of them. These are basically which differences are between the schedulers regarding the queue size or the priming instructions, so the instructions that we need to fill the queue. Second question is what measurement methods are practical for modern processors, especially Zen 3 and 4? And which schedulers can leak non-repeatable events, for example, keystrokes? And fourth question is, well, can we somehow also exploit scheduler contention remotely by using JavaScript? So let's start with the first research question. So what are the differences between the schedulers, the queue sizes, and the priming instructions? There are multiple requirements for priming instructions. So we have to be able to delay them so that they can occupy a slot in the scheduler queue for a controllable time. They also have to be targeted, meaning that, well, okay, the instruction has to be decoded into at least one micro-op that can be handled by only a single execution unit. Furthermore, they must be single queue, meaning that they may only cause contention on a single scheduler queue and not multiple ones. They also have to be non-serializing because, as we see later, we exploit out-of-order execution here, and serializing instructions would just destroy that. Furthermore, for exploitation from a regular user space program, the instruction has to be unprivileged. Yeah, because otherwise we might just have other means to exploit the machine. You might now ask, well, okay, why don't you just look it up in the manual? The problem here is, well, the manual at that point is, as we found out, outdated, incorrect in several ways, which can be seen here. There's this moveD instruction, which is considered to go to ALU2, but as we found out, goes to ALU0 instead. And there are several occasions of that. So we had to reverse engineer that. For details about that, you can look it up in the paper. What did we figure out in the end? Well, okay, there are priming instructions for scheduler 2 of the integer execution unit, which is the store SB instruction. And similar for scheduler 3, there's also the load SB instruction that can be used to prime that scheduler. For the FPU, it's a little bit more complicated because basically we were not able to prime a single scheduler here. There is this diffSD instruction, which is documented to go only to scheduler 0, but we figured out that it actually uses both of them. So while we cannot prime a single scheduler of the FPU, we are still able to prime the entire FPU. And about the capacity, well, okay, here we figured out that available information is actually correct. So each of the integer schedulers has 24 entries. Each of the FPU schedulers has a capacity of 32 entries. And in front of there is this non-scheduling queue, which has a capacity of 64 entries. Now we come to the second research question, which is what measurement methods can we use on modern processors? Prior work measured the capacities using non-serialized timer reads, and they only observed a capacity of 22 microops when the actual capacity is in fact 24 microops. So the question is basically, well, where did the 2 microops go? Why weren't they able to observe that? We developed a new method to measure scheduler contention, which is called bingo race. This is based on having a second thread that just generates numbers all the time and stores them in memory, in shared memory somewhere. There's no particular requirement on the numbers that are generated. They just are required to not repeat frequently, so they have to generate a long sequence of unique numbers. So how does it work? Well, okay, first of all, we drain the pipeline just as prior work did. Then similar to prior work as well, we have a dependency chain. In that case, delayed by a square root SD instruction, which then is converted into an integer. Then we draw the first bingo number. Then we prime the scheduler queue by using k repetitions of the priming instruction. In that case, well, okay, it's also a multiplication here. And then we draw the second bingo number. So what happens now? If we do not exceed the capacity of the scheduler, then the second read of the bingo number is reordered, meaning that in our case here, our 13 and our 14 contain the same bingo number. And for the other case, if we exceed the capacity, well, then we get a pipeline stall, and our 14 is not equal our 13. And the nice thing here is that this actually results in the correct capacity on all the microarchitectures we tested. You can also see here at 20 microops, from 20 to 21, there's this increase when we execute a busy loop on the sibling thread. And this, again, reveals the watermark mechanism just as prior work has also observed. But why do we get the correct capacity approach and not with the hardware timer reads or performance counters? Well, we did tests with a neutral instruction after the last multiplication and before the second bingo read. And there we observed that basically Zen 3 and Zen 4 stall when we exceed 22 entries anyway. It just takes a little while. And that's basically the reason why prior work observed a lower capacity. Even though the neutral instruction goes to a completely different scheduler, we always see this delayed stall also if we exceed 22 entries. Why does it work? Our bingo approach, well, basically the reading from the bingo variable is faster than reading the hardware counter. So the CPU has a little bit of time to actually complete that. And this doesn't happen with the hardware timer read. Now we go to research question 3, where we asked which schedulers can leak non-repeatable events, for example, keystrokes. Turns out basically all of the integer ones. How did we examine that? So we have an attacker process that we co-locate to the victim process, and then we repeat the following. So basically we check whether we can exceed the watermark limit on a certain scheduler without causing backend stalls. We record the result of our test. So if we could exceed it, then there was no activity on the sibling thread, meaning that the victim was idle. Otherwise, the victim was busy, and we record a timestamp for that. That's basically all we do. And if we do that on the GDM3 login manager, you see the following. So we have here our key press event. Then we see a burst of activity for a certain period of time. And this repeats for the next keystroke as well. So we can easily detect the keystrokes by finding the start of such a burst, by filtering out bursts that are not big enough to be related to the keystrokes. This works quite well, as you can see here on the table. So we have Only in the case of scheduler 0, we have false positive here when doing 100 keystrokes. Also a very low standard deviation of our times, meaning that we can detect the keystrokes quite precisely. Interestingly, this worked the best for scheduler 3, where we had a standard deviation of below 1 millisecond. And now the fourth and final research question: can we also exploit scheduler contention remotely by using JavaScript? Turns out, yes, we can, but there are several challenges I want to discuss a little bit now. So first question is, well, okay, which scheduler can we target from JavaScript? It turns out that JavaScript has this math imul function, which causes the JIT compiler to basically emit imul instructions directly, so we can directly prime scheduler 1. The other thing is, well, okay, we don't have direct control over the JIT-generated machine code. We used several techniques to address that. First of all, we used asm.js syntax, which basically gives some hints to the JIT compiler, which data types we are dealing with. For delaying our input parent, we used the math square root function. And in order to prevent the JIT compiler from over-optimizing our measurement code, we pseudo-randomized the operands for the square roots and the multiplications. We don't have any direct access to hardware timers, but this is already solved by bingo measurement that I have just shown before. Next question is how to achieve co-location between the sender and the receiver. We solved that by creating multiple receiver web workers. On our machine, which has 16 threads, we created 14 receivers, meaning that one thread is left over for the sender and one thread is left over for the bingo thread. Then the operating system just distributes them over the available cores. Here's a small demo of that. So we receive, and in the sender we just send hello world. And you can see here that we actually received that message. Then for our evaluation of the covert channel, so we have a raw bandwidth of 1 kilobit per second, which is basically caused by a time-slice-based approach. Then we have quite low error rates, below 1.5%, resulting in true capacities of around 890 bits per second for SEN3 and 940 bits per second for SEN4. That's it from my side. If you have any questions about that, please contact me, given the contact data here. Thanks.